we're going to talk about how to predict some of these charges that ions form. This will mainly be a predictive tool for what are known as the main group elements. If you recall, on the periodic table, there are main group columns, which are typically those that have the letter A at the top. And then there are the transition metals that are in that center section that have columns that start with B. So this predictive tool is really for main group, with some exceptions. And this is also for what we refer to as monatomic ions. Monatomic meaning these ions are just one atom of an element that is charged. Let's recall that metals will form cation ions. Metals will become positively charged. Non-metals will form anions in ionic compounds and become negatively charged when in the presence of a metal, of a cation. Metalloids, for the most part, we are considering to. Is that always true? Not always, but for this class, for right now, yes, that's true. So the main thing is going to be, we're going to use our periodic table. Okay, we're going to use the column headings on our periodic table to predict what ion charge the element will be. If you recall, I showed an example in a previous video of a sodium being willing to give away 1 electron and a chlorine being willing to accept 1 electron. How do we predict that? Some of it can be predicted based on a theory of bonding called Lewis theory. If you've talked about that in your class, that's great. If you haven't talked about that before, that's okay too. Lewis theory is a bonding theory that is basically based on the number 8. Elements are trying to form bonds in order to give themselves 8 valence electrons. That's 8 electrons in their highest outside electron energy level. So we can use the group number and our knowledge of if it's a metal or a non-metal to predict the charge, because the group number actually is the number of valence electrons for these main group elements. So in group 1A, those are your alkali metals, right? Group 1A, these will become +1 cations because they're metals. So you may want to take your copy of the periodic table and a pen or pencil and just write above it, right above the column, +1. Okay. Hydrogen is a little bit of an exception, as hydrogen usually is. Hydrogen can be +1 in some compounds like acids that we'll see. It can be -1 if it's the nonmetal in an ionic compound, like we'll make some time look at metal hydrides. But all the metals will become +1. So that is how I knew that sodium would be a +1 ion. So the format for writing ion symbols is very much like what I did right over here. So here's an example. A sodium ion is written symbol of the metal and then the charge as a superscript next to it. You can write the number 1 if you want to. It is typically not written. We usually just write if it's plus or minus. We get it higher numbers, then we write the number. The name of this for cations is just the name of the element, and then we might also include the word ion if to be specific that we're talking about when it's charged. So we would say that's the sodium ion as opposed to the sodium, the element. Moving along. Group 2A, alkaline earth metals are going to form +2 cations. Let's just think, what does that mean? As the metal, it is willing to give away some number of electrons. These elements in group 2A will give away, transfer 2 electrons. They become +2 charged. Calcium. Calcium, when it is in an ionic compound and it's made an ion, will be +2. Calcium ion. Skip for now all of this stuff, the transition metals, okay? These are really not as predictable except for 3, which I'll share with you in a second. These are not predictably one charge, okay? So come over to group 3A. The metals in group 3A, so be sure you know what is a metal in group 3A. If you look at 3A, that very first element, boron, that's not a metal. That's a metalloid. Remember, this is for metals. This is the charge of metals. We're going to look at nonmetals. These will be +3 cations. So, for example, aluminum, Al3+. It would just be named the aluminum ion. That's its name. If you are wondering if it's important if you write the number and then the symbol, this is traditional, number first and then positive or negative, but it doesn't really matter. Group 4A is a little different. There are metals in group 4A down at the bottom of the column, but they are not predictable. So I'm going to skip those for right now, and we'll come back to them in a different video. What I do want to tell you are these other predictable cations, predictable positive ions that you will find here in the transition metals. So these, again, are predictable transition metals. Most are not predictable, but these 3 are. Okay? You need to maybe mark to yourself on your sheet. In group 1B, you can predict confidently that silver will always be a +1 charge. Okay? So that's just called the silver ion. You can also predict in group 2B, so very next one right next to it, zinc, when it's an ion, is always +2. And right below that, cadmium, when it's an ion, is always +2. These are predictable charges for these ions. Okay. Now, since this is where we leave metals behind, moving left to right on the table, and now we're into nonmetals, we know that nonmetals form anions, negatively charged. So I said we're going to skip group 4A. There's too many exceptions. It's not predictable enough. But if I look at group 5A, which in some classes you may be required to know are called the nictogens. Maybe your teacher did or didn't need you to know that. So we're in group 5A, and we're looking at our nonmetals, starting with nitrogen, phosphorus. Those elements in group 5A have 5 valence electrons on them already. What they're looking to do is gain enough electrons to give them 8 outside total. So anything in group 5A that's a nonmetal will become a -3 anion. It will gain 3 electrons. These anions, okay, the symbol is written the same way, but the name changes a little bit. For these monatomic ions, okay, monatomic meaning just one atom. These are what we find on the periodic table. An anion's name changes in the ending of it. So, for example, N3- is no longer just neutral nitrogen atom, it's an ion. N with 3 extra electrons is now called the nitride ion. It is not the nitrogen ion. It is the nitride ion. This is how anion name endings change. Anion name endings change. And then group 6A starts with oxygen, sulfur. Your professor may have wanted you to know these are sometimes called chalcogens. Again, these have 6 valence electrons. They are wanting in an ionic compound to gain 2 from a metal ion somewhere. So the -2 charge. So something like oxygen. There's a formula for its ion symbol. And the name would then, of course, be not the oxygen ion, but the oxide ion. Or if you had sulfur, it would not be the sulfur ion, it would be the sulfide ion. Group 7A, which everybody is expected to know that these are called halogens, already have 7 valence electrons, just like chlorine did a little bit ago, and it is wanting to gain 1 more from a metal cation source. And so this is where we get, for example, chloride. When we talk about table salt, NaCl, that is why the name is not sodium chlorine. The name is sodium chloride, because this is getting into rules for naming these ionic compounds. The metal cation name is just the name of the element. The anion name changes the ending to ide. And just to be clear, what about those group 8A? Those noble gases. This element, these elements, these don't form ions, period. They do not join up in compounds with metals. They don't do it. Occasionally, you can have a big noble gas like xenon form a covalent compound, but even that's kind of rare, okay? Group 8A metals, non-metals, noble gases, are not interested in making bonds. They, for the most part, have 8 valence electrons already. They're happy with that. They're not interested in sharing or transferring. So there's a quick review on how to predict ion charges for metals and non-metals using the periodic table.